252 million years ago, the ocean was almost empty. 96% of its marine species had disappeared in less than 60,000 years, leaving the largest vacancy the ocean had ever experienced. The reefs were gone. The seafloor communities that had survived for hundreds of millions of years had been devastated. The old predators were gone with them. For a brief moment, the largest ocean on Earth had almost nothing left to hunt, and then something walked into it. The first animals entering this ruined sea had never been marine predators before. Their ancestors had been living on land when the extinction happened. There was almost no competition waiting for them, no established hierarchy, no familiar rules. And evolution moved into the empty spaces. Within roughly 2.5 million years, one of these new marine lineages had already begun producing animals that would eventually reach enormous sizes. One descendant grew to roughly 17 meters, nearly 56 feet, becoming one of the fastest examples of extreme body size evolution ever documented in a marine lineage. But size was only one answer. Another early Triassic reptile developed something far more unusual. Its entire body became enclosed in a complete bony tube, not armor over part of the body, a structure that surrounded the animal almost completely. No other vertebrate in the history of life evolved the same solution. Something in this recovering ocean had already made extreme protection worthwhile. Then there was another animal that took the opposite approach. Instead of relying on powerful eyes to find prey, it hunted with a strange bill-like structure, feeling its way through shallow water much like a platypus. For decades, fossils of this animal gave scientists an incomplete picture because the specimens were so often missing their heads. And somewhere in this same rebuilding ocean, evolution discovered another strategy that would appear again much later in Earth's history: filter feeding. The same basic solution that baleen whales would independently evolve roughly 200 million years afterward. The ocean had been nearly destroyed. Then it became a laboratory. Animals entered empty ecological spaces and began experimenting with bodies, senses, armor, size, and entirely new ways of finding food. Within only a few million years, the silence was beginning to disappear. The predators were returning. The competition was returning, and the ocean was becoming dangerous again. If you're tucked in right now, phone dimmed, trying to let your brain slow down, this one was made for you. Give it a like, subscribe if you haven't. It's free, and it helps our channel more than you can imagine. And let me know in the comments, where are you watching from, and what time is it where you are? Let's return to the ocean when almost nothing was left. Before the first signs of collapse, the Permian Sea had the settled complexity of an ecosystem that had been refining itself for hundreds of millions of years. Around 260 million years ago, the ocean was not a single familiar basin, but a planetary system wrapped around Pangaea. Panthalassa occupied most of the surface beyond the supercontinent, extending toward both poles, while the warm Tethys Sea opened along its eastern margin. Currents moved through immense distances, connecting habitats that differed in depth, temperature, light, and chemistry. Across the shallower seafloors, reefs formed the physical framework of this world. Rugose and tabulate corals, lineages that have no living descendants, built layered structures that rose above the surrounding sediment. Their skeletons created crevices, ledges, sheltered chambers, and exposed surfaces, turning bare seafloor into crowded neighborhoods. Small animals could cling to the reef, hide within it, graze across its surfaces, or hunt among its passages. The reef was therefore more than scenery. It was architecture, and architecture determined where life could live. Beyond those structures, Brachiopods were among the most familiar inhabitants of the Permian seafloor. Their paired shells opened and closed around soft bodies that filtered nourishment from the surrounding water. For roughly 500 million years, brachiopods had persisted through repeated changes in climate and ocean chemistry, surviving four earlier mass extinctions and returning again and again to abundance. By the late Permian, hundreds of species occupied seafloors across different depths and latitudes, their shells forming part of the texture of the ocean floor itself. Among them moved trilobites, armored arthropods, whose lineage stretched back roughly 270 million years. By this late stage of their history, they were no longer the extraordinary variety of forms seen in earlier eras, yet they remained part of the living community. Their segmented bodies crossed the sediment, their compound eyes registering movement and light, while their long evolutionary history placed them among the most enduring animals ever to inhabit the sea. Above the bottom, ammonoids filled another layer of the ecosystem. Their coiled shells contained chambers that controlled buoyancy, allowing them to move through open water rather than remaining tied to the seafloor. Some were small, others considerably larger, and their diversity reflected a broad range of feeding strategies. They were active participants in the food web, both hunters and prey, connecting smaller organisms to larger predators. Other hunters occupied still higher levels. Sharks moved through the water with bodies already shaped for efficient predation. Armored fishes carried protective plates over their heads and trunks. Cephalopods occupied several sizes and ecological roles, while ancient echinoderms lived across the bottom in forms that would look unfamiliar beside their modern relatives. Sea scorpions, though no longer the giants of earlier periods, remained part of a much older predatory heritage. Taken together, these animals formed something more intricate than a collection of species. Energy passed upward through many connected pathways, from microscopic producers to grazers, filter feeders, scavengers, hunters, and the predators that hunted them. Habitats were layered vertically as well as horizontally. The water column belonged to different creatures at different depths, while the seafloor offered its own sequence of niches. Every structure had occupants, and every occupant was embedded within relationships shaped over geological time. This was the inheritance of more than 300 million years of marine evolution. It had survived earlier catastrophes and absorbed countless smaller changes without losing its essential architecture. Then the Siberian traps began releasing enormous quantities of volcanic gases, and the chemistry of the planet started to shift. Temperatures rose, oxygen availability changed, and seawater chemistry became increasingly hostile. The transformation unfolded with extraordinary speed. In less than 60,000 years, the vast majority of marine species disappeared. The world that remained was not a damaged version of the same ocean. Its foundations had been removed. An empty ecological niche is not simply a place with fewer animals. It is a missing function, a role in the living machinery of an ecosystem with no organism left to perform it. After the Great Dying, the ocean contained gaps at almost every level. The animals that filtered nourishment from the water were greatly reduced. Shellfish crushers had lost much of their former diversity. Open water pursuit predators were scarce, and the larger hunters that once controlled the upper levels of the food web had largely vanished. In a functioning sea, these roles are rarely available for long. A young species entering open water encounters established predators, established prey, and competitors already shaped by generations of selection. A shellfish crusher must compete with other shellfish crushers. A small hunter must survive among larger hunters. Even an animal with an unusual body form faces an ecological landscape filled with organisms already adapted to exploit the same resources. Opportunity exists, but it is contested. The aftermath of the extinction changed that balance. A creature arriving in a newly opened habitat could encounter resources without meeting an equally specialized rival. An unfamiliar feeding structure might persist long enough to become useful. A body shape that would normally be eliminated by competition could instead provide access to food that no other animal was efficiently using. Evolution had not become directionless. Natural selection still favored survival and reproduction, but the number of available paths had suddenly multiplied. This condition is known as ecological opportunity. It becomes especially powerful when an ecosystem loses many competitors at once, because surviving and newly arriving lineages can expand into functions that were previously occupied. The early Triassic Ocean offered an unusually large experiment in this process. The extinction had removed so much biological structure that evolution was no longer working inside the crowded framework inherited from the Paleozoic. It was rebuilding that framework while the environmental conditions remained difficult. Those conditions mattered. The water was still affected by elevated temperatures, fluctuations in oxygen availability, and unstable chemistry associated with the continuing consequences of volcanic activity. The vacancy, therefore, did not mean an easy ocean. It meant an ocean in which almost every lineage faced severe environmental stress, while also encountering unusually little biological competition. Survival depended first on tolerance. Once a population established itself, however, the ecological space around it could be remarkably open. That combination created a peculiar evolutionary landscape. The same empty food web could be approached from different directions by unrelated survivors. One lineage could exploit suspended food particles, another could specialize in hard shelled prey, while another moved into open water as an active hunter. Each strategy altered the opportunities available to the others, gradually creating new relationships where almost none had existed before. The fossil record preserves the result as a sudden appearance of different marine groups across the early Triassic. New forms emerge in close geological succession, carrying specialized structures that indicate very different ways of living. Some were built for pursuit, others for suction feeding, crushing, filtering, or life close to the seafloor. Their differences are important because they show that the rebuilding was not a single evolutionary march toward one successful design. Instead, several lineages were exploring the same newly opened world at once. The ocean was becoming an evolutionary landscape filled with experiments, each shaped by whatever resource remained accessible. Competition would return as populations expanded, and every successful innovation would eventually create new pressures for something else to overcome. For a brief interval, though, the boundaries that had governed marine life for hundreds of millions of years had been loosened, allowing an entirely new ecological order to take form. The first inhabitants of the recovering ocean were not newcomers. They were remnants, scattered representatives of lineages that had endured the catastrophe and emerged into conditions unlike anything their ancestors had experienced. During the Griesbachian stage, from roughly 252 to 251 million years ago, the sea remained biologically diminished, but life had not disappeared. A narrow collection of survivors occupied the spaces left behind, and their particular tolerances would shape the character of everything that followed. Bivalves were among the earliest beneficiaries. Clams, mussels, and their relatives had once lived alongside the far more abundant brachiopods, usually occupying a secondary position on the seafloor. Now their former competitors were greatly reduced, and bivalves could spread across sediments, hard surfaces, and shallow habitats with comparatively little resistance. Their generally lower metabolic demands help some species endure reduced oxygen, while their shells and physiology offered advantages under changing seawater chemistry. What had been a supporting cast of the Permian seafloor began assuming a much larger role. Gastropods followed a similar path. Snails had survived the extinction in greater proportions than many other marine groups, and their flexible diets allowed them to exploit resources that had become available in the disrupted ecosystem. Some grazed across exposed surfaces, scraping organic material from rocks and sediments. Others consumed detritus or small organisms. Their mobility gave them access to habitats that no longer belonged to a stable community of specialized competitors. Then there were the conodonts, small eel-like animals whose bodies were soft except for intricate feeding elements made from calcium phosphate. That mineral mattered in a sea where changing chemistry could dissolve calcium carbonate structures more readily. While many shelled organisms struggled, conodont feeding elements were comparatively resistant, allowing these animals to persist through the environmental upheaval. Their abundance made them important small predators, moving through the lower levels of the food web and feeding on other small organisms. The ammonoids presented a different kind of survival. Their lineage had once included hundreds of species, but only a handful of genera are thought to have crossed the extinction boundary. These survivors were not yet the abundant, diverse swimmers that would later fill the water column. During the earliest Triassic, they remained limited, holding on to a place in open water while conditions continued to fluctuate around them. Their survival was therefore less a triumph than a continuation, a few branches remaining, attached to a lineage that had nearly been cut away. On the seafloor, some echinoids endured as well. Their spiny bodies and mobile feeding habits gave them a degree of ecological flexibility, allowing surviving species to move across substrates and exploit whatever food remained available. Certain fishes also crossed the boundary, including representatives of ray-finned fishes and sharks. Their diversity had been reduced, but their presence preserved fragments of older predatory and feeding strategies. Together, these survivors formed an ecosystem of unusual simplicity. There were fewer layers between predator and prey, fewer specialized interactions, and far fewer competitors occupying the same resources. Yet, the survivors were physiologically diverse enough to begin reshaping the available habitats. Bivalves spread across the bottom, gastropods grazed and scavenged, conodonts hunted among smaller organisms. Ammonoids remained in open water, while fishes and sharks retained portions of their former roles. Their importance lay not in grandeur, but in inheritance. Every lineage that survived carried biological information accumulated before the catastrophe, but each now faced opportunities that had scarcely existed in the older ocean. The survivors had passed through the narrowest gate imaginable, and the ocean beyond it belonged to them. A few coils of shell remained when the rest of the ammonoid world had fallen away. Those surviving lineages entered the earliest Triassic carrying a body plan already suited to open water, but almost none of the diversity that had once surrounded it. Their shells still turned through successive chambers, each new compartment added as the animal grew, while the living creature occupied the outermost chamber. For a time, only a handful of ammonoid genera persisted, scattered through a sea whose food web was still being rebuilt. Their position in the water column gave them an unusual advantage. Unlike animals tied to the seafloor, ammonoids could move through open water, avoiding some of the severe oxygen depletion that affected deeper sediments and bottom habitats. They could follow concentrations of prey, shift with changing conditions, and occupy different depths as the recovering ocean changed around them. Their buoyant shells also allowed them to remain suspended without constantly swimming upward, making the water column a three-dimensional habitat rather than a simple corridor. Generation followed generation, and small differences had room to accumulate. Ammonoids reproduced more rapidly than many larger marine animals, giving natural selection repeated opportunities to favor changes in shell shape, growth, feeding, and movement. In a crowded ecosystem, such differences might have led only to another species competing for an already occupied resource. Here, the possibilities were broader. A change that allowed one population to exploit a different depth or prey type could establish an entirely new ecological position. During the Denarian stage, roughly 251.2 to 250.8 million years ago, the first signs of expansion became visible. New genera appeared, and the surviving branch of the ammonoid family tree began dividing into forms that no longer resembled a single narrow remnant. Then came the Smithian stage, when the pace accelerated dramatically. Dozens of genera emerged in rapid succession, followed by a remarkable increase in species diversity. The shells recorded this expansion with extraordinary detail. Some became more tightly coiled, others broader or more elongated. Chamber proportions changed, ornamentation shifted, and shell geometry became increasingly varied. These differences were not merely decorative. Shell architecture influenced buoyancy, swimming efficiency, stability, and the depths an animal could occupy. Across generations, modifications to the shell opened different ways of living, allowing related ammonoids to separate themselves through the water column. Their spread was equally remarkable. Smithian ammonoids occur across the scattered continents and oceanic regions of the Triassic world, giving paleontologists fossils that can be compared between rock formations separated by vast distances. Their shells now appeared in rocks formed far from one another, evidence that this radiation was not confined to one sheltered basin. The same broad evolutionary expansion was unfolding across the recovering Panthalasan realm, turning a once restricted survivor into a worldwide presence. Because individual species appeared and disappeared within relatively narrow intervals of geological time, their shells became precise markers for identifying the ages of sedimentary layers. A particular ammonoid could effectively place a piece of ancient seafloor within a small slice of deep time. In this way, the animals that once drifted through the recovering ocean became instruments for reconstructing its history millions of years later. The result was a reversal, almost without parallel. A lineage reduced to perhaps 2 or 3 surviving genera did not merely recover its former variety. At the height of the Smithian radiation, ammonoids reached greater taxonomic richness than they had possessed during the Permian. Their success transformed the open water into a shifting mosaic of related hunters, each adapted to slightly different conditions, each occupying space made available by the catastrophe. What began as a few surviving coils had become a branching evolutionary network. The ammonoids were no longer simply remnants of an older ocean. They had become one of the principal architects of the new one. The shoreline had become an evolutionary boundary. And then, almost imperceptibly in geological time, that boundary began to dissolve. Reptiles that had spent generations adapted to air, weight, and solid ground started entering water that offered resources with remarkably little competition. Their ancestors had returned to land from aquatic origins hundreds of millions of years earlier, so this was not a simple return. It was a new transformation, requiring terrestrial bodies to become something the ocean could carry. Before the extinction, such an invasion would have faced formidable resistance. Marine predators already controlled open water, Specialized animals occupied the seafloor, and established feeding strategies left little room for an unfamiliar reptile. Entering the sea meant confronting organisms perfected by millions of years of selection. The newly altered ocean presented a different arrangement. Many of those established competitors were gone, leaving ecological roles available across the entire water column. That opportunity appeared while the environment itself remained difficult. Warm water, unstable oxygen levels, and changing chemistry imposed severe limits on survival. Yet those pressures affected every potential colonist. A reptile capable of remaining submerged for longer periods could exploit prey that land animals could not reach. An individual with slightly denser bones could resist buoyancy. A limb that became broader and more rigid could push against water rather than support weight on land. Small changes accumulated into an entirely different way of moving through the world. The earliest marine reptiles appear in the fossil record remarkably soon after the extinction, within roughly 1 to 2 million years. Their remains do not describe a single cautious lineage making the transition alone. Instead, several distinct reptile groups were already exploring marine habitats, suggesting that the ecological opening was broad enough to attract independent experiments at nearly the same time. Southern China preserves some of the clearest evidence of this transformation. During the early Triassic, parts of what is now Hubei province lay beneath warm, shallow seas, spread across carbonate platforms and sheltered lagoons. These environments offered a combination of relatively shallow water, abundant small prey, and protected coastal settings. For an animal still divided between land and sea, such habitats could provide a gradual route into aquatic life without requiring an immediate commitment to the open ocean. The anatomical changes preserved in these early reptiles reveal how rapidly that commitment could develop. Limbs became increasingly paddle-like as the bones and digits changed their proportions. Bodies lengthened and streamlined, reducing resistance as animals moved through water. Bone density increased in some forms, providing ballast that helped keep the body submerged. Feeding structures changed as well, with jaws and snouts becoming suited to prey that lived in water rather than on land. What makes the transition especially unusual is its repetition. Ichthyosaur relatives were not the only reptiles entering the sea. Sauropterygians followed a separate evolutionary path, while other experimental groups developed their own combinations of limbs, armor, feeding structures, and body proportions. The same ecological opening was therefore being approached by multiple lineages, each arriving with a different terrestrial inheritance. Some became coastal hunters, others moved toward open water predation. Still others evolved feeding methods that had no close equivalent among their land-dwelling ancestors. Their bodies preserve the gradual negotiation between two environments, with old structures being modified rather than simply discarded. Within a geological interval, measured in only a few million years, the shoreline had become the starting point for a new marine radiation. The reptiles entering the water were not returning to an ancient home. They were constructing a new one, adapting their inherited bodies to an ocean whose vacant ecological spaces made experimentation unusually possible. Imagine the early Triassic marine world not as a finished ecosystem, but as a workshop where the tools were still scattered across the floor. In the shallow seas of what is now southern China, reptiles appeared in forms that seem almost improvised, each body carrying a different answer to the problem of living in water. The Nanjing Yuanan fauna preserves this unusual collection with remarkable clarity, revealing at least 7 distinct marine reptile species sharing the same broad region while pursuing very different ways of life. One animal might have been built to crush hard prey, while another moved through the water as a pursuit hunter. Elsewhere, a long snout or expandable throat opened another possibility, allowing an animal to seize food through suction rather than speed. Still, another lineage explored filter feeding, gathering tiny organisms from the water instead of chasing individual prey. These strategies were not variations on a single successful design. They represented separate experiments unfolding within the same newly reorganized sea. The anatomy of these reptiles often preserves traces of their terrestrial inheritance. Some retained proportions or structures that would have been useful on land, even as their limbs, bodies, and feeding systems became increasingly aquatic. Their bones record gradual adjustments rather than instant perfection. A paddle could begin as a modified walking limb, a dense skeleton could provide ballast, a streamlined trunk could reduce resistance. Each alteration changed what the animal could do, and each new ability opened another part of the marine environment. A study published in 2015 found that the diversity of feeding strategies among early marine tetrapods reached an extraordinary peak soon after their appearance. Filter feeding, lunge feeding, suction feeding, shellfish crushing, and active pursuit predation were all represented within the early Triassic radiation. Such variety suggests that ecological opportunity did more than increase the number of species. It encouraged different lineages to explore fundamentally different solutions to obtaining energy. The Nanzang Yuanan animals also reveal something important about evolutionary experimentation. A successful body plan does not emerge fully formed. It is assembled through generations, tested against changing conditions, and sometimes abandoned. The Hupehsuchians, including forms with heavily reinforced bodies, occupied specialized positions that later disappeared. Certain early ichthyosauromorphs followed paths that ended near the boundary between the early and middle Triassic. Their extinction did not erase the significance of their existence. Each represented a biological possibility that had been tried in a world where such possibilities were unusually accessible. Other experiments lasted longer. Their descendants became the foundations of the great marine reptile radiations that would eventually dominate Mesozoic seas. The refined ichthyosaurs of later Triassic waters, the sauropterygians that eventually produced plesiosaurs, and other specialized marine predators inherited evolutionary lessons from these early forms. Their later success was built from anatomical groundwork established when the marine environment was still being assembled. What makes this early fauna especially valuable is its concentration of alternatives. Instead of seeing one lineage gradually perfecting a single strategy, the fossils preserve multiple branches exploring different directions at nearly the same time. The result resembles a natural archive of evolutionary trial and error, with bodies shaped for speed, ambush, suction, filtering, crushing, and other forms of feeding. For a short geological interval, the sea allowed possibility itself to become visible in anatomy, leaving behind fossils that record not only survival, but the remarkable variety of paths evolution could explore. Most of these early experiments eventually disappeared. The ocean changed, competition intensified, and environmental pressures shifted. Yet their fossils preserve a rare interval when marine evolution was unusually unconstrained, and when several different answers could coexist before the emerging ecosystem began deciding which ones would endure. The fossil was small enough to fit within the span of a human arm, yet its bones preserve one of the most delicate transitions in the history of marine life. Cartorhynchus lenticarpus lived about 248 million years ago, roughly 4 million years after the extinction, in what is now Anhui Province in China. When its nearly complete skeleton was recovered from a limestone quarry near Chowhu in 2011, it offered something paleontologists had been missing for decades: a body caught partway between terrestrial ancestry and permanent life in the sea. Its name carries a clue to the feature that made it so valuable. Cartorhynchus lenticarpus refers to a shortened snout and flexible wrist, and the wrists were unlike those of later, fully aquatic ichthyosaurs. They retained enough movement to support the animal while moving across solid ground. The front limbs were already broad and flipper-like, but their construction still allowed a degree of terrestrial motion. An animal with such limbs could enter shallow water, swim, and then return to a shoreline without abandoning either environment completely. The skeleton was only about 40 centimeters, roughly 16 inches, long. Its size makes the evolutionary transformation easier to picture. This was not a giant predator entering the open ocean. It was a small reptile negotiating the margins, carrying a body still suited to more than one kind of surface. The broad limbs would have helped it move through water, while its flexible joints preserved the mechanical possibility of hauling itself across land. That combination suggests a creature spending much of its life in shallow coastal settings, where water and exposed ground remained close together. Its bones reveal another adaptation. Cartorhynchus had unusually dense, heavy bones compared with terrestrial reptiles, a condition known as pachyostosis. Extraskeletal mass could reduce buoyancy, helping the animal remain submerged without spending constant energy resisting the tendency to float upward. For an early swimmer living around shallow coastal waters, that added weight may have been useful. The body was becoming better suited to immersion, even while the limbs retained traces of a land-based past. The head carried a different clue. Instead of the long, narrow snout that would characterize many later ichthyosaurs, Cartorhynchus had a short, constricted muzzle. Its anatomy suggests suction feeding, in which rapid expansion of the mouth and throat draws water and prey inward. This method would have allowed a small animal to gather food from close range without depending on the speed and precision required by an open water pursuit hunter. Later examination of the skull also revealed rounded teeth positioned within the jaws, probably suited to handling hard-shelled prey. What makes the animal important is not that every detail of its life can be reconstructed. Some aspects remain uncertain, including exactly how often it came ashore and how it moved there. Its significance lies in the combination of features preserved together: large flippers, flexible wrists, dense bones, a short snout, and a feeding system suited to water appear in one animal, forming a physical record of transition rather than an imagined sequence. Before this discovery, the ichthyosaur fossil record largely presented the lineage after it had already become marine. The terrestrial ancestor was known, and the fully aquatic descendants were known, but the intermediate stage was missing. Cartorhynchus occupied that space in both time and anatomy within this ancient record alone. Its fossil, therefore, captures something evolution rarely leaves so clearly behind. Not the beginning or the finished form, but the interval between them, when an animal could still belong to the shore and the sea at the same time. The first clue was not in the body, but in the shape of a missing head. For decades, Hupehsuchus was known from fossils whose skulls had not survived, leaving paleontologists with a strange, heavily built marine reptile and an incomplete picture of how it fed. Then, newly discovered skull specimens from the Jialinjiang Formation of Hubei province changed that picture. The animal had first been recognized in 1972, but its feeding anatomy remained uncertain for decades. Described in 2023, They revealed an animal whose anatomy points toward one of evolution's most remarkable recurring solutions. Hupehsuchus nanchangensis lived roughly 247 to 249 million years ago and reached about 1 meter, roughly 3 feet, in length. Its body was rigid and compact, with limbs adapted for movement through water, yet it lacked the sleek construction expected of a fast pursuit hunter. The skull told a different story. Its snout was long, narrow, and toothless, formed from elongated, strap-like bones that remained arranged around a slender channel running along the front of the jaws. Along the edges of those jaws were grooves and notches that may have supported soft tissues capable of straining food from water. The jaws themselves were unusually flexible in their connection to the skull, allowing the mouth to expand and draw in a substantial volume of water. Taken together, these features suggest a feeding system based not on biting individual prey, but on gathering enormous numbers of tiny organisms suspended in the sea. The resemblance to baleen whales is striking because the two lineages were separated by an immense span of time. Baleen whales would not evolve until roughly 200 million years later, long after Hupehsuchus had disappeared. They also came from entirely different branches of the vertebrate tree, yet both arrived at a similar arrangement, a broad intake of water followed by the retention of small prey. In the whale, flexible baleen performs the filtering. In Hupehsuchus, the precise soft tissues have not been preserved, but the skull anatomy provides evidence for a comparable function. This is called convergent evolution. It occurs when unrelated organisms independently arrive at similar biological solutions because they encounter similar demands. Wings evolved separately in insects, birds, and bats. Streamlined bodies appeared in creatures as different as fish, reptiles, and mammals. Here, the repeated solution was filtering small prey from open water, a task that rewards a large intake of water, specialized filtering structures, and a body capable of moving efficiently while feeding. The timing gives the resemblance an even deeper significance. The filter feeding communities that had once occupied the Permian Sea had been drastically reduced, leaving abundant microscopic food with far fewer animals adapted to harvest it. Hupehsuchus appears in the early Triassic, only a few million years after the extinction, close enough to place its evolution within the period when marine ecosystems were still being assembled. The opportunity was present, and an unusual reptile made use of it. Hupehsuchus did not become the ancestor of whales, and its resemblance to them is not evidence of hidden kinship. Instead, it reveals something more subtle about evolutionary possibility. When an ecological problem appears, the number of workable solutions may be smaller than the diversity of life suggests. Across hundreds of millions of years, in completely separate lineages, the same empty space can call forth remarkably similar designs. A reptile in the early Triassic had already discovered a feeding strategy that later became one of the defining adaptations of the largest animals ever to live in the ocean. The resemblance was not inherited, it was reinvented. There was a peculiar kind of hunter moving through the shallow Triassic lagoons, one that seemed to have little use for the world above the water. Eretmorhipis caroldongi carried a long, rigid body, 4 swimming flippers, and rows of bony plates along its back. Yet its most important equipment was concentrated at the front. Its skull was remarkably small, while its snout broadened into a flat, flexible bill, unlike anything previously known from a marine reptile. The animal lived roughly 250 million years ago in what is now central China, within shallow lagoons spread across a carbonate platform. These waters may have been only about 1 meter, roughly 3 feet, deep, creating an environment where a bottom-feeding animal could move close to the seafloor. Eretmorhipis was about 70 centimeters, roughly 28 inches, long, small enough to slip through these sheltered habitats while searching among the sediment for shrimp, worms, and other invertebrates. Its eyes provide the most unusual clue. They were exceptionally small compared with the rest of its body, suggesting that vision had become a secondary sense rather than the principal way this animal found food. Instead of relying on sight, Eretmorhipis appears to have used its broad bill to explore the water and sediment around it. The structure resembles the bill of a modern platypus, a resemblance produced not by ancestry, but by two separate evolutionary histories arriving at a similar solution. A platypus uses its bill as a sensory instrument, detecting signals from prey concealed beneath the surface. Eretmorhipis may have employed comparable touch-based hunting, with sensitive tissues around the bill, helping it locate small animals hidden in the lagoon floor. Scientists have also considered mechanoreception, the detection of pressure changes in surrounding water, as a possible part of its sensory system. Electroreception, the detection of weak electrical fields produced by living organisms, has been proposed as another possibility, although direct evidence for that ability in Eretmorhipis remains limited. What makes the animal especially revealing is the combination of traits preserved in its skeleton. The four flippers provided steady movement through shallow water, while the stiff body and protective plates suggest an animal built for a particular style of life rather than rapid pursuit. Its anatomy does not resemble an unfinished version of some later marine reptile. It represents a complete ecological solution, assembled from different pieces of anatomy and directed toward a specialized way of finding food. The first fossils of Eretmorhipis were discovered without complete heads, leaving its biology difficult to interpret. Later specimens preserving the skull transformed that picture. When the nearly complete remains were studied, the tiny eyes and broad bill revealed a sensory strategy unlike the familiar, vision-driven hunting of many reptiles. In 2019, a detailed study in scientific reports brought this unusual animal into clearer view. The deeper significance lies in its timing. Only a few million years after the greatest marine extinction in Earth history, a reptile was already occupying a sensory niche that required no powerful jaws, rapid swimming, or large eyes. The lagoon offered a different kind of opportunity, prey concealed in sediment and water where touch could outperform sight. More than 240 million years later, a mammal on the opposite branch of the tree of life would arrive at an uncannily similar design. Eretmorhipis and the platypus were never relatives in the sense required to inherit the same bill from a shared specialized ancestor. Their resemblance arose independently, shaped by the same physical problem and the same useful answer. In the early Triassic, even the senses themselves were becoming experimental territory, and the ancient lagoons were already rewarding animals that could perceive the world in ways their predecessors had never needed. The body of Parahupehsuchus longus was built around an idea that no vertebrate had ever tried before. Instead of shielding only part of itself, this small marine reptile enclosed its entire trunk within a rigid bony tube. Found in Yunnan County in Hubei Province, China, and described in a 2014 study, it measured about 50 centimeters, roughly 20 inches in length. Its armor was not decorative. It was a complete structural response to a sea where something had begun hunting other marine reptiles. The tube formed from expanded ribs and belly ribs, known as gastralia, which overlapped and fused into a cylindrical casing around the body. At its deepest, the protected trunk measured about 6 centimeters, roughly 2.5 inches from the upper surface toward the belly. Nothing comparable is known anywhere else in vertebrate history. A turtle shell may seem like a distant parallel, but turtles construct their armor through a transformation of the body wall itself, while Parahupehsuchus arrived at protection by turning ribs into a surrounding cage. Additional armor covered its back. 3 layers of dermal ossicles, small bones embedded within the skin, were arranged into an interlocking surface. Beneath them lay triangular plates, while larger flat bones stretched across several vertebrae, creating another layer of protection above the already enclosed trunk. The result was a creature whose body carried armor over armor, an arrangement that must have imposed costs on movement, growth, and energy. Every layer represented tissue that had to develop, mineralize, and be carried. Evolution does not usually preserve such expensive equipment without a reason. A rigid tube could restrict the flexibility needed for swimming, add substantial weight, and complicate the mechanics of breathing. For an animal living in water, where efficient movement matters, those disadvantages would have been significant. Yet, the anatomy suggests that whatever danger existed around Parahupehsuchus was sufficient to make protection worth carrying. The surrounding fossils give that armor a context. The same rock formation contains at least one sauropterygian reptile large enough to have hunted Parahupehsuchus, along with several other marine reptiles that show different degrees of defensive construction. Some were protected by smaller bony structures, while others carried more elaborate barriers between themselves and potential attackers. These fossils describe more than a collection of unusual bodies. Together, they record a community in which predators and prey were already influencing one another's evolution. This is especially important because the predators themselves were changing. The first marine reptiles had entered an ocean where many old ecological roles had vanished, but an empty food web could not remain empty forever. As new hunters began consuming marine tetrapods, prey animals faced a new kind of pressure, one created not by the ancient predators of the Permian, but by reptiles that had only recently become inhabitants of the sea. The emergence of marine tetrapod-eating marine tetrapods marked a new layer in the ocean's structure. Predators were no longer simply feeding on the remaining invertebrates and small fish. Some were becoming hunters of other reptiles, creating a trophic relationship that had not previously existed in the marine fossil record. Parahupehsuchus belonged to this changing world, and its extraordinary armor preserves the response of prey to that new danger. Within only a few million years, the ocean had acquired predators capable of making other marine reptiles their food, and prey capable of answering with a body unlike any vertebrate before or since. The bony tube of Parahupehsuchus was therefore more than a shield. It was a record of an ecosystem becoming intricate enough for evolution to turn predation into an architectural problem. At first, the Ichthyosaur lineage was hardly recognizable as the dynasty it would become. Cartorhynchus moved between shore and sea with a body only about 40 centimeters, roughly 16 inches, long, its flexible wrists still capable of supporting weight beyond the water. Nothing in its proportions suggested an animal destined to dominate the open ocean. Yet, within the same lineage, another possibility was already taking shape, one that would transform a small amphibious reptile into one of the most formidable hunters the ancient seas had produced. As generations passed, the compromises of living between land and water began to disappear. The wrists became more rigid, transforming the limbs into dedicated flippers. The hind limbs diminished as their usefulness on land declined. The body became increasingly streamlined, while the skeleton changed internally, with denser bones helping control buoyancy during sustained swimming. Each modification represented another step away from the shoreline. Eventually, there was less reason to return to land, because the sea itself had become the environment in which these animals were most successful. By the Spathian stage of the early Triassic, roughly 250 to 247 million years ago, ichthyosauriforms were no longer represented by a single experimental design. Several genera had appeared, accompanied by different body shapes and feeding systems. Some carried broad, crushing teeth suited to hard-shelled prey. Others developed elongated snouts, lined with conical teeth for capturing fish. Still, others reduced their teeth, apparently adapting toward softer prey and different feeding mechanics. The lineage was not simply becoming larger, it was spreading through the available ecological space. Then size began changing on a different scale. Fossils from South Primorye in the Russian Far East preserve ichthyopterygian remains from the early Spathian, including a humerus belonging to an animal estimated to have reached about 5 meters, roughly 16 feet, in body length. That places a substantial marine reptile remarkably close to the beginning of the ichthyosauriform radiation. In evolutionary terms, the distance between a small shoreline animal and a predator several meters long had been crossed with extraordinary speed. Body size matters because becoming large is not merely a matter of growing more tissue. A giant marine predator needs enough food to support its metabolism, a body capable of moving efficiently through water, and an ecosystem capable of sustaining its position at the top. The early Triassic Ocean was beginning to provide all three conditions. Ammonoids were multiplying through the water column, fish populations were recovering, and invertebrates were occupying newly established communities across the seafloor. Food was becoming abundant at precisely the moment large marine predators were beginning to appear. The pace becomes clearer when ichthyosaur evolution is compared with the later transformation of whales. Both lineages began with terrestrial ancestors and eventually produced enormous marine predators, yet ichthyosaurs reached giant body sizes faster than whales did. Their acceleration was unusually rapid even by the standards of major evolutionary transitions, suggesting that the ecological conditions of the early Triassic were unusually favorable to large marine hunters. There was no established giant predator controlling the upper levels of the food web, and the expanding prey base offered an immense reservoir of energy. Each increase in size could open access to prey that smaller hunters could not efficiently exploit, while improved swimming ability allowed these animals to search broader regions of the ocean. Selection therefore favored not one isolated trait, but a connected transformation of the entire body. The result was an evolutionary ascent from a small reptile testing the boundary between shore and sea toward animals whose descendants would command the open ocean. The shoreline had been the starting point, but the expanding food web was becoming something different, a vast environment where speed, size, and specialized hunting could finally be rewarded on an oceanic scale. There is a moment in the fossil record when size itself seems to change its meaning. In the Augusta Mountains of Nevada, a skull emerged from rocks that were once part of the ancient seafloor, and its proportions belonged to an animal far removed from the small reptiles that had only recently entered the sea. Symbospondylus young Aurum lived about 246 million years ago, and its remains record one of the swiftest increases in body size known from marine vertebrates. The skull alone measured about 2 meters, nearly 6½ feet, long, a span comparable to the length of a grand piano. From that immense head extended a body estimated at about 17 meters, roughly 56 feet, making this animal comparable in overall length to a modern humpback whale. Yet its ancestors had been remarkably modest. The oldest proposed relatives of ichthyosaurs appeared only about 249 million years ago, with bodies less than a meter long, less than about 3 feet. In roughly 2.5 million years, that lineage had produced a predator more than an order of magnitude longer. Nevada did not resemble the landscape that occupies the region today. During the Triassic, this part of western North America lay along the eastern margin of Panthalassa, an immense ocean whose waters covered the region where the Augusta Mountains now rise. The limestone and other marine rocks preserved there are fragments of an ancient seafloor, holding traces of an ecosystem that had formed remarkably soon after the extinction. Symbospondylus carried an elongated snout lined with conical teeth, suggesting a diet that included fish and squid. Its size also opened another possibility. A predator reaching about 17 meters, roughly 56 feet, could potentially overpower smaller marine reptiles, placing it among the earliest vertebrates capable of occupying the role of a true megapredator. The distinction matters because the ocean was not merely recovering species by species, it was rebuilding relationships that had almost entirely disappeared before. Entire levels of the food web were being rebuilt at once. Researchers studying the fossil hill fauna found that this community already contained a surprisingly intricate network of predators and prey. Its structure could resemble aspects of modern marine ecosystems, despite having assembled in less than 8 million years from a starting point of profound ecological loss. Large predators, smaller hunters, invertebrates, and abundant prey were becoming connected into a functioning system, each new lineage altering the opportunities available to the others. The speed of Symbospondylus was especially striking when compared with whales. Baleen whales required a much longer evolutionary history to reach comparable dimensions, even though modern oceans possess extraordinarily productive food webs supported by abundant microscopic plankton. Many of those highly productive plankton communities had not yet developed in the Triassic. The ichthyosaurs therefore seem to have reached enormous size under conditions that should have made such growth difficult. Part of the answer may lie in what the extinction had removed. A large body requires energy, but an empty food web also creates opportunity. With few established predators occupying the largest ecological spaces, selection could favor animals capable of exploiting prey at scales that had previously belonged to extinct lineages. Symbospondylus was not simply a larger version of its ancestors. Its size changed the boundaries of what it could hunt, where it could travel, and which part of the recovering ocean belonged to it. In the space of a few million years, the first giant had appeared, turning a lineage born at the margins of the sea into one of its largest inhabitants. By the time Thalatoarchon moved through the Triassic Sea, the meaning of being large had changed. It was no longer simply an advantage for reaching scattered prey. Size had become a way of controlling an entire layer of the recovering ocean. Thalatoarchon's saurophagus appeared about 244 million years ago in the seaway that covered what is now Nevada, carrying a skull built for a very different kind of hunting. Its estimated length exceeded 8 meters, about 28 feet, placing it among the largest predators known from this stage of marine recovery. Yet, the most revealing feature was not its length. It was hidden between the jaws. Unlike the rounded or conical teeth common among many ichthyosaurs, the Thalatoarchon possessed laterally compressed teeth with sharp edges on both sides. They were cutting instruments, suited to slicing flesh rather than simply gripping small prey. That distinction changes the picture of how the animal lived. A fish can be seized and swallowed whole, but a large marine reptile presents a different problem. Its body is too substantial to take in at once, and its limbs or tail can turn the encounter into a prolonged struggle. Cutting teeth offer another solution. They allow a predator to remove manageable pieces from prey that cannot be swallowed whole, opening an ecological pathway toward hunting animals of comparable scale. The name Thalattoarchon saurophagus translates as lizard-eating, sovereign of the sea, a description that fits the animal's place within this developing community. Its role has been compared by researchers with that of the modern orca, another predator capable of pursuing and killing large marine vertebrates. The comparison is ecological rather than genealogical. These animals are separated by immense stretches of evolutionary history, yet both occupy a position where the predator itself becomes a major force shaping the behavior and distribution of other large animals. What makes the Nevada discovery especially important is the timing. Earlier in the Triassic, marine tetrapods were still exploring the mechanics of life in water and dividing newly available resources among unfamiliar body plans. By about 244 million years ago, one of those lineages had reached the uppermost level of predation. A four-limbed vertebrate had entered a position that had previously been dominated by large predatory fishes. The shift was more than a change in body size. It marked a reorganization of the food web. Thalattoarchon lived among smaller ichthyosaurs, ammonoids, fishes, and other marine reptiles, creating several levels of predator and prey within the same seaway. Energy could move from small organisms into larger hunters, and then upward again into a predator capable of consuming substantial vertebrate prey. Such a structure requires more than a few surviving species. It requires enough ecological stability for many interactions to persist together. The rocks of the Favorite Canyon region preserve this transformation in fragments of bone and tooth. But those fragments describe a larger pattern. The ocean had begun with survivors occupying whatever spaces remained available. Now it possessed a predator whose existence depended on the presence of a complete community beneath it. Thalattoarchon could only become sovereign after the sea had rebuilt enough life to support a hunter at its highest level. Its double-edged teeth, therefore, record something deeper than feeding anatomy. They mark the moment recovery had produced competition, pursuit, and predation on a grand scale. The rebuilt ocean was no longer merely inhabited. It had acquired a hierarchy, and at its highest point moved a reptile capable of hunting the rulers of every lower layer, within a seaway that had only recently begun rebuilding its ecological complexity. Along the margins of the recovering sea, another reptilian experiment was taking shape, separate from the swift bodies moving through open water. The Sauropterygians arrived by a different evolutionary route, carrying a body plan unlike that of the Ichthyosaurs, and finding opportunity in places where broad coastal shallows offered shelter, prey, and room to expand. Among the earliest members of this lineage was Nothosaurus, a predator built for the margins rather than the distant pelagic realm. Its long, narrow skull held sharp teeth that interlocked when the jaws closed, forming an effective trap for fish. Depending on the species, some Nothosaurus reached about 2 meters, roughly 6½ feet, while larger forms approached 4 meters, about 13 feet. They were substantial animals, yet their hunting grounds kept them apart from the open water specialists. The distinction was written into their bodies. Nothosaurus possessed limbs suited to swimming, but it was not yet a completely ocean-bound reptile. Its anatomy suggests that it could leave the water and haul itself onto land, retaining a connection with the shoreline even as its life became increasingly aquatic. In this respect, it represents another stage in the great return of reptiles to the sea, but one following a separate path from the early ichthyosauriforms. Coastal water offered a different collection of possibilities from the open ocean. Reefs, sheltered embayments, shallow platforms, and uneven seafloors created habitats where pursuit could happen at close range, and where fish and smaller marine animals could gather. A predator that could swim efficiently while remaining capable of using the shore had access to both aquatic and terrestrial environments, allowing natural selection to work across a broader landscape of resources. This separation of habitats helped several reptile lineages coexist without immediately collapsing into direct competition. Ichthyosaurs were becoming increasingly specialized for life in the open water, while sauropterygians explored the edges, where depth was limited and the relationship between land and sea remained fluid. The distinction was not absolute, and different species surely overlapped in their diets, but the broad division gave each lineage room to develop its own anatomy, behavior, and rhythm of life along the ancient coast. Nothosaurus also reveals how quickly the coastal zones were being reorganized. A shoreline predator no longer had to resemble the reptiles that had lived there before the extinction. The opportunity was new, and the anatomy could be reshaped around it. Limbs became more useful in water, bodies became streamlined, and skulls became increasingly suited to seizing aquatic prey. Each generation carried another small adjustment, and over geological time, those adjustments accumulated into a body increasingly committed to the sea. The later history of sauropterygians would extend far beyond these early coastal hunters. Their lineage eventually produced plesiosaurs, including forms with long necks and broad flippers that became familiar inhabitants of Jurassic and Cretaceous seas. The elegant marine reptiles of those later worlds were not sudden inventions. Their ancestry reached back to much more modest animals working along Triassic shores. What matters in this early stage is the independence of the invasion. The recovering ocean did not receive a single reptilian replacement for the creatures that had vanished. It became a field of opportunity, entered by several unrelated or distantly related groups, each approaching the water from a different direction. Ichthyosaurs occupied one part of that expanding realm, sauropterygians another, and the boundary between land and sea became a place where evolution could explore forms that had scarcely existed before. The ocean was rebuilding not through one lineage, but through many, each finding its own passage into the spaces left behind. A long neck can make an animal seem almost unreal, especially when the neck extends far beyond the body carrying it. Along the shores of the Middle Triassic Sea, Tanystropheus lived with precisely such an anatomy. In the larger species, the total body length reached about 6 meters, nearly 20 feet, while the neck stretched to roughly 3 times the length of the torso. It was rigid rather than flexible, built from elongated vertebrae arranged into a structure that seems less like a conventional neck than a narrow bridge extending toward the water. For more than a century, that structure resisted a simple explanation. Fossils of Tanystropheus had been examined since the 19th century, yet its way of life remained uncertain. Some interpretations placed it on land, where the long neck might have reached vegetation. Others imagined an aquatic animal moving through open water. The anatomy seemed capable of supporting several possibilities, and without evidence of its meals, the animal remained suspended between them. That changed when exceptionally preserved remains provided traces of what had passed through its digestive system. A study, published in 2020, showed that the larger species had consumed fish and cephalopods. The evidence placed Tanystropheus firmly within the marine food web, where its unusual proportions could be understood as part of a hunting strategy rather than an anatomical curiosity without purpose. Its body was not shaped for prolonged pursuit. The stiff neck would have made rapid turning difficult, while the elongated structure offered another advantage. Tanystropheus could keep much of its body near the surface or along a sheltered bank, extending its head over the water and reaching prey without bringing its entire mass into view. An ambush strategy would have allowed the neck to function as a long-range feeding arm, carrying the jaws toward fish and cephalopods before the rest of the animal needed to move. Yet the same architecture that created this advantage also exposed a weakness. A long, rigid neck is difficult to shield, and the Middle Triassic Sea contained predators large enough to exploit that vulnerability. Two Tanystropheus fossils preserve an extraordinary record of such encounters. Their skulls were separated from their bodies by bites that left the neck broken and the head removed. The spacing and size of the wounds point toward powerful marine predators, with Nothosaurus and Symbospondylus among the proposed attackers. These fossils offer something unusually intimate in the geological record. They do not merely show that predators and prey occupied the same ecosystem. They preserve the physical consequence of one marine reptile attacking another. The broken connection between skull and spine becomes evidence of behavior, revealing that predation had advanced beyond fish and small invertebrates into a world where reptiles themselves had become part of the hunt. Tanystropheus, therefore, belonged to an ocean whose recovery was becoming increasingly complex. Its long neck opened one feeding opportunity, but that opportunity existed inside a network of larger hunters, competing reptiles, and vulnerable prey. Every adaptation carried a cost, and every advantage could become a weakness when another animal evolved a way to exploit it. Its unusual form was therefore not an isolated experiment. It belonged to a broader pattern in which recovering marine ecosystems rewarded specialization while exposing specialized animals to new dangers. The more completely the food web filled, the more precisely each creature had to fit within it. The decapitated remains capture that balance with unusual clarity. The sea was no longer simply filling empty spaces. It was becoming an arena of interacting strategies, where a neck built to reach farther could also become the very feature that brought a predator close enough to strike. For a brief interval after the Great Extinction, the ocean did not merely regain inhabitants, it rebuilt relationships. By the Middle Triassic, roughly 247 to 237 million years ago, marine communities contained feeding layers that reached from microscopic producers to animals capable of hunting other large reptiles. The Nevada fossil hill fauna, together with the Luoping and Panchen biotas of southern China, preserves different pieces of this newly assembled structure, revealing an ecosystem no longer defined by absence. At its foundation were primary producers, converting energy into the organic material that sustained everything above them. Invertebrates consumed that production, while small predatory fish and cephalopods hunted among them. Above those layers came marine reptiles occupying several different roles. Some crushed shelled prey, others pursued fish, while still others drew water into their mouths to capture small organisms. Filter feeding appeared beside suction feeding and lunge feeding, creating a remarkable range of solutions within an ocean that had only recently been stripped of much of its former complexity. The arrangement was also unusually top-heavy. Scientists use that term to describe an ecosystem in which predators occupy a larger share of the living community than expected, relative to the abundance of prey beneath them. The pattern reflects an uneven recovery. Some predator lineages expanded rapidly into open opportunities, while many groups that once supported the older Permian food web had not returned in comparable numbers. The result was an ocean where hunting strategies diversified with extraordinary speed, and where several levels of the food chain were occupied by reptiles at once. Among the most revealing fossils is a Middle Triassic ichthyosaur, containing the remains of a thalattosaur about 4 meters, about 13 feet, long. The stomach contents preserve something more than a meal. They show that marine tetrapods had begun consuming prey of a scale approaching that of the largest animals familiar from human experience. Such predation required more than specialized jaws. It required enough energy moving through the ecosystem to support hunters large enough to take substantial vertebrate prey. It also reveals that predator and prey were no longer separated into simple categories. A hunter could become food for something larger, while its own presence altered the behavior and abundance of animals below it. That structure had no obligation to resemble the Permian Ocean that came before it. The species had changed. The ecological relationships had changed, and the pathways by which energy moved through the community had changed with them. A filter feeder could occupy space once held by another organism with a completely different body plan. A reptile could become a mid-level hunter, while another lineage rose toward the top and began feeding on animals that were themselves predators. Recovery was therefore not a return to an earlier arrangement. It was the construction of a new one. What makes the timing especially remarkable is the compression of the entire process. The extinction occurred approximately 252 million years ago. By around 244 million years ago, only about 8 million years later, complex communities had developed multiple feeding levels, specialized predators, large-bodied hunters, and apex relationships. The ocean had moved from ecological emptiness toward a densely connected system in a span that is almost invisible beside the age of Earth. Within those layers, every creature became part of several relationships at once, consuming one organism, competing with another, and remaining vulnerable to something larger. The food web had become complete not because life had returned to what it was, but because evolution had filled the vacant spaces with an entirely different cast of animals. The change can be traced not only through the bodies of predators, but through the defenses of the animals they pursued. Across the early Triassic seafloor, survival began leaving a different signature in shells, burrows, limbs, and body coverings. The ocean was becoming a place where remaining exposed carried a greater cost, and evolution began answering that pressure in countless small ways. Paleontologists call this long transformation the Mesozoic Marine Revolution, a sustained rise in predation intensity that began during the Triassic and continued through the Jurassic and Cretaceous. Its importance lies not in one predator or one prey species, but in the relationship between them. Marine reptiles brought active pursuit into ecosystems that had been dominated by slower forms of hunting. Their air breathing allowed repeated excursions through the water column, while increasingly streamlined bodies gave them the ability to search, chase, and strike across greater distances. Predation became a moving force rather than something encountered only at close range. The response appeared among the animals being hunted. Marine invertebrates increasingly developed thicker shells, stronger defensive structures, greater mobility, and deeper burrowing habits. Each feature carried a cost in material or energy, yet those costs could become worthwhile when predators were capable of finding and breaking through older defenses. The fossil record, therefore, preserves an ecological conversation written in anatomy. A thicker shell reflects more than construction. A deeper burrow represents more than shelter. Together, They reveal prey, adapting to a world in which the margin for exposure had narrowed. Bivalves became especially important in this changing landscape. They had survived the extinction and expanded into ecological spaces once occupied more heavily by brachiopods. During the Triassic, many bivalve lineages evolved stronger shells and more substantial hinges, while some adopted deeper burrowing strategies that placed their bodies farther beneath the sediment. The movement downward was itself a form of defense, shifting the encounter between hunter and prey into a different physical environment. At the same time, crustaceans were diversifying into forms with increasingly capable grasping appendages. Early relatives of crabs and lobsters brought another kind of pressure to the seafloor, using movable claws to handle and break potential prey. Shells that resisted one predator could face another, while animals buried beneath sediment still existed within a world of hunters searching for concealed food. Defense was no longer a single solution. It was becoming part of a layered ecological contest. This escalation changed the meaning of adaptation. A shell could become stronger because a predator had become more capable. A burrow could become deeper because searching behavior had improved. Greater mobility could become valuable because remaining in one place had become increasingly risky. None of these changes required evolution to move toward a predetermined design. They emerged from repeated interactions, generation after generation, as every advantage created pressure for another response. The process did not end when the Triassic Ocean matured. Through the Jurassic and Cretaceous, predators and prey continued refining their respective strategies. Shells became more elaborate, burrowing became more specialized, swimming grew more capable, and new defensive structures appeared. Some animals developed chemical defenses, while others relied on speed, camouflage, armor, or living beneath the reach of hunters. Much of the marine life surrounding us today still carries traces of that ancient escalation. The thick shell of a mollusk, the buried existence of a seafloor animal, or the defensive chemistry of an invertebrate belongs to a lineage shaped by pressures that intensified after the Great Dying. The ocean had not simply received new inhabitants. Its rules of survival had changed, and the higher intensity established during the early Triassic became a lasting foundation for marine evolution. For hundreds of millions of years, two kinds of shellfish shared the seafloor, but they did not share its future. Brachiopods had occupied marine habitats since the early Paleozoic, filtering food from the water while anchored to the sediment in enormous numbers. Their shells became one of the most familiar signatures of ancient seabeds, preserved across continents and through repeated changes in climate, geography, sea level, and the slow rearrangement of continental margins. Bivalves lived beside them throughout this long interval, yet remained comparatively secondary, filling similar spaces without becoming the dominant architects of seafloor communities. The end Permian extinction altered that balance with extraordinary permanence. Brachiopods lost a catastrophic proportion of their diversity, and the surviving lineages never returned to their former ecological abundance. Bivalves, by contrast, emerged with far greater representation and began spreading through the spaces that had suddenly become available. Clams, oysters, mussels, and their relatives were not simply taking advantage of empty real estate. Their physiology happened to fit the chemistry of the recovering ocean more effectively. That distinction matters because the transition was not primarily a contest between two groups struggling directly for the same resources. Statistical studies comparing their evolutionary histories indicate that bivalves did not simply defeat brachiopods through superior competitive ability. The decisive filter came from the environment itself. After the extinction, seawater chemistry was altered. Oxygen was scarce in many settings, and acidity created additional physiological stress. Animals that could tolerate those conditions had an advantage before competition between survivors even became important. Bivalves generally required less oxygen to sustain their metabolism and were better able to endure acidic conditions than brachiopods. In an ordinary ocean, such differences might have remained subtle, almost hidden within the broader range of biological variation. In the aftermath of the extinction, they became consequential. The chemistry of the water selected which bodies could continue functioning, which could reproduce, and which could expand into newly available habitats. Survival was therefore shaped by an environmental test that neither lineage had designed and neither could control. As conditions stabilized, bivalves multiplied into roles once heavily occupied by brachiopods. Some lived attached to hard surfaces, others burrowed into sediment, and still others occupied mobile or semi-mobile positions on the seafloor. Their ecological flexibility allowed them to spread through coastal shelves and deeper marine environments, gradually establishing a new pattern of benthic life across habitats that had once belonged largely to brachiopods. Brachiopods persisted, but increasingly as specialized survivors in habitats where their physiology remained viable. Their decline was therefore not a gradual fading, but a sudden narrowing of the ecological world in which they could thrive. Their former abundance became a memory preserved in stone. The change established during the Triassic never reversed. Bivalves have remained major components of marine seafloors ever since, while brachiopods survive today in a much smaller collection of cold, deep water refuges. The boundary between these worlds represents more than a change in which shellfish became common. It marks the transition from the Paleozoic evolutionary fauna toward the modern evolutionary fauna, a reorganization in which entirely different groups came to structure the living surface of the seafloor. Every mussel attached to a rock, every oyster growing in a coastal bed, and every clam beneath beach sand belongs to an ecological order shaped by conditions that existed roughly 252 million years ago. Their dominance was not simply the reward for being stronger competitors. It emerged because, when the chemistry of the ocean became unusually harsh, their bodies were better suited to remain within it. The ancient seafloor changed its inhabitants, and in doing so, it changed the ecological character of every ocean that followed. Some of the most important witnesses to the ocean's recovery were small enough to disappear into the scale of the larger creatures around them. Conodonts were eel-like animals, their bodies soft and slender, with one remarkable exception. Inside their mouths were arrays of mineralized structures called conodont elements, tiny tooth-like pieces made from calcium phosphate. Unlike the calcium carbonate shells and skeletons that were vulnerable to the altered chemistry of the post-extinction seas, these elements were comparatively resistant to dissolution, allowing their remains to survive where much larger fossils could vanish. That chemical resilience gave conodonts an unusual place in the recovering ocean. They were not merely survivors preserved by favorable mineral composition. During the early Triassic, they became among the most abundant small predators in marine communities, moving through the food web somewhere between the smallest fish and the larger hunters that had begun returning to the sea. Their feeding structures were suited to capturing soft-bodied prey, while their own bodies became food for animals higher in the growing hierarchy. Their importance was therefore ecological as well as geological, woven into the developing network of predation that was rebuilding across the ocean. Because their mineralized elements were so durable, conodonts also left an unusually continuous record through changing environments, even when other evidence of the same communities became fragmentary. A thin layer of sediment could preserve a sequence that outlasted the shells, bones, and larger bodies once living above it. Yet their greatest legacy came from something even smaller than their bodies: the changes recorded in those mineralized elements. Conodont populations evolved rapidly, producing successive forms whose shapes, proportions, and arrangements changed through relatively brief intervals of geological time. As one species disappeared and another emerged, the sediments beneath ancient seas accumulated a sequence of biological markers. Each layer could carry a distinctive assemblage, giving later geologists a way to recognize where it belonged within the unfolding history of the Triassic. This practice is known as conodont biostratigraphy, the use of changing fossil species to establish the relative ages of rock layers. Because conodont species could appear and vanish so rapidly, their distributions provide a degree of temporal resolution rarely available from larger marine animals. Some early Triassic intervals can be distinguished on timescales of only tens of thousands of years. Rocks, separated by thousands of kilometers, can therefore be compared through the tiny remains of animals that once inhabited the same ancient ocean. That precision has allowed scientists to place major stages of recovery into a much firmer sequence. The expansion of marine reptiles, changes in ocean communities, and later disturbances can be compared against conodont zones, turning scattered exposures of ancient seabed into parts of a shared chronology. A fossil only a fraction of the size of the creatures that ruled the water can consequently tell us when those giants appeared, disappeared, and changed their surroundings. The irony of their history is that conodonts survived the Great Dying only to encounter another boundary much later. Their lineage continued through the Triassic, adapting through changing seas and evolving new forms until it disappeared during the end Triassic extinction approximately 201 million years ago. After that boundary, conodont elements vanish entirely from the younger fossil record. Their disappearance leaves the early Triassic suspended between two extinctions, but their surviving remains continue to mark the passage of time between them. In the rocks, each tiny element becomes a point on an immense geological calendar, preserving the order of events with a precision that the larger animals themselves could never provide. The predators may have rebuilt the ocean, but the conodonts gave its recovery a measurable rhythm, one fossil layer at a time. For decades, the first chapters of the Triassic recovery were pictured as an ocean stripped almost to its foundations, with only sparse communities scattered through the aftermath. Then, beneath southeastern Idaho, a layer of stone began telling a different story. The Paris biota, preserved in rocks dating to about 250 million, 600,000 years ago, records a marine community only roughly 1.3 million years after the main extinction boundary. Yet its inhabitants reveal a world far more intricate than the old picture allowed. At least 7 major branches of animal life occur within the assemblage, together with 20 distinct orders of animals. Such diversity does not resemble a simple biological holding pattern. It suggests several feeding relationships, different body plans, and ecological roles already operating within the same ancient sea. The fossils are especially valuable because many were preserved with enough detail to reveal anatomy rather than merely presence, allowing the community to be read as an ecosystem instead of a list of survivors. Among its most remarkable inhabitants were gladius-bearing coleoid cephalopods, distant relatives of modern squid and octopuses. Their presence in these rocks pushes their known history much deeper into the Triassic than expected. The next firmly documented appearance of comparable forms comes roughly 50 million years later in the Jurassic. That enormous interval had once looked like a missing chapter in cephalopod evolution. The Parasbiota placed part of that lost history back into view, showing that sophisticated marine lineages could already exist while recovery was still young. Another surprise came from sponges. Leptomatid sponges were previously known from much older rocks of the Cambrian and Ordovician, more than 200 million years before this community existed, and had been presumed extinct long before the Great Dying. Their appearance in the Parasbiota makes them a Lazarus taxon, a lineage that vanishes from the fossil record for a prolonged interval before appearing again. Such returns do not necessarily mean the animals truly disappeared from every ocean. They can instead reveal how incomplete the fossil record becomes when populations retreat into places where preservation is rare. The same layer contains crinoids and brittle stars, whose anatomical features suggest that certain evolutionary innovations appeared earlier than scientists had once believed. Their presence adds another dimension to the discovery. Recovery was not simply a matter of surviving species, slowly increasing in number. In some places, evolution was already experimenting with new structures and new ecological possibilities, while much of the wider ocean remained severely disrupted. Geography helps explain how such an unexpected refuge could exist. During the early Triassic, southeastern Idaho lay along a mid-latitude region of the vast Panthalassa Ocean, away from the most intensely heated equatorial waters. Conditions there may have been more favorable for complex marine communities to persist and reorganize. The rocks, therefore, preserve neither an untouched ocean nor an ocean fully restored. They capture something more nuanced, a regional refuge embedded within a planet still recovering from extraordinary ecological loss. The Parasbiota does not erase the evidence for widespread devastation. Instead, it changes the shape of the recovery itself. The ocean was not uniformly empty, and evolution did not proceed at one steady pace everywhere. In certain places, only a little more than 1 million years after catastrophe, ancient lineages returned to view. Unexpected predators and prey shared the same waters, and forms once thought separated by immense stretches of geological time appeared together again. Beneath the stone of Idaho, the recovery becomes less like a straight line and more like a scattered pattern of life, appearing wherever the changing earth allowed complexity to take hold. Recovery did not rise steadily from the ruins of the Great Dying. Beneath the apparent return of diversity, the early Triassic remained unstable, and another environmental disturbance came close to undoing much of what evolution had rebuilt. During the Smithian stage, ocean temperatures climbed again after a brief interval of cooling, creating a second thermal crisis that spread through marine communities already living close to their limits. The Smithian thermal maximum brought another period of intense warming, with equatorial sea surface temperatures approaching or exceeding levels that many organisms could tolerate. As the water warmed, oxygen became more difficult to retain, and oxygen-poor regions expanded through the ocean. The disturbance was not simply a repetition of the original extinction. It arrived in a world that had already lost much of its former diversity, leaving fewer lineages capable of absorbing another major environmental shock. Ammonoids reveal the scale of the setback with unusual clarity. Across the Smithian stage, 53 genera are known from the fossil record, representing a substantial radiation after their earlier losses. Yet when the crisis passed and the Spathian stage began, only 4 genera are known to have survived. An entire radiation had been reduced almost to its foundation again, leaving a handful of lineages to repopulate an ocean that had only recently begun filling with life. Conodonts followed a similar path. These small animals had become important members of the recovering marine ecosystem, and their rapidly changing mineralized elements were preserving the sequence of geological time. During the Denarian and early Smithian, their diversity was comparatively broad. After the Smithian crisis, only two species are known to have persisted into the Spathian. The very fossils that allow scientists to trace the recovery were themselves recording another near collapse within the recovery. The underlying causes had not disappeared. The carbon cycle remained disturbed, temperatures continued to fluctuate at dangerous levels, and oxygen depletion remained a persistent threat. Deep beneath what is now Siberia, volcanic activity associated with the Siberian traps was still releasing enormous quantities of material into the atmosphere. Roughly one-third of the total volcanic volume erupted after the main extinction boundary, extending the environmental disturbance well into the period when marine ecosystems were attempting to reorganize. For evolution, repeated collapse created an unusual kind of filter. Each crisis removed organisms from communities that had already been reduced, leaving survivors to rebuild from a narrower biological foundation. When radiation followed, it did not begin with the full range of forms that had existed before the disturbance. Fewer species remained, and the surviving populations carried only part of the variation that had once been available. The next generation of ecological experiments therefore started from a more restricted starting point. This process could shape evolution for millions of years. A lineage entering one crisis with several possible body plans might emerge with only a few, and those survivors would become the ancestors of later diversification. Another crisis could narrow the field again. Over time, repeated filtering could steer entire groups toward particular forms, feeding strategies, and ecological roles that were partly determined by which branches happened to endure each environmental bottleneck. The Smithian crisis therefore leaves the recovery without a simple upward curve. The ocean was rebuilding, but beneath that rebuilding lay repeated contractions, each one thinning the branches of life before new growth appeared. Between extinction and stability, the distance remained remarkably small, and for a time, the future of the Triassic Ocean rested with only a few surviving lineages. The sea had reached a rare moment of fullness when the Smithian stage drew toward its end. Marine reptiles were diversifying, ammonoids had reached their highest known early Triassic richness, and conodonts occupied the waters in forms that recorded an expanding biological world. Then the pattern changed again. Around 250 million years ago, another environmental crisis moved through the ocean, leaving behind a distinct extinction horizon, now recognized as the end Smithian extinction. Its arrival was marked by renewed warming, expanding oxygen-poor waters, and disturbances in the carbon cycle. Carbon isotopes shifted as the atmosphere and ocean responded to another pulse of environmental change. The pattern echoed the Great Dying, though on a smaller scale. Yet scale alone does not determine consequence. A community that has only recently rebuilt its diversity can be vulnerable even to a disturbance far smaller than the catastrophe that came before it. The timing made the loss especially significant. The Smithian had represented the high point of early Triassic marine diversification, a period when many lineages were experimenting with new forms and feeding strategies. Across the sea, communities had become increasingly elaborate, with predators occupying higher positions and prey adapting to the growing pressure. The fossil record from the boundary shows how abruptly that complexity could contract. Rich and widely distributed faunas gave way to a more limited collection of survivors, with diversity falling and the geographic pattern of marine communities changing alongside it. Ammonoids provide one of the clearest traces of this narrowing. During the Smithian, their radiation had produced dozens of genera, yet only 4 genera are known to have crossed into the Spathian. These were not simply 4 names left behind in a fossil catalog. They represented 4 surviving branches from which later ammonoid diversity would grow. The vast variety of ammonites that eventually inhabited Jurassic and Cretaceous seas descended from lineages that passed through this narrow evolutionary doorway. Such a reduction is known as an evolutionary bottleneck, a severe decline in population size that leaves later generations with only part of the genetic diversity present beforehand. When populations contract this sharply, the future is shaped not only by adaptation, but also by chance. Traits carried by the survivors become disproportionately important because there are fewer alternative forms remaining. Evolution continues, but it continues from a smaller inheritance. The contrast also reveals how misleading a simple recovery curve can be. A rise in species numbers does not mean an ecosystem has become secure. Diversity can accumulate, while ecological resilience remains fragile, especially when many organisms share the same environmental dependencies. The Smithian community had become richer, but that richness had not yet been given enough time to develop the redundancy that allows mature ecosystems to absorb severe disruption. One environmental shift could therefore remove entire branches of the new food web at once. The Spathian radiation that followed was therefore not simply another repetition of the earlier recovery. Researchers have found evidence that its diversification proceeded more slowly than the earlier Dianirian radiation, consistent with a biological starting point that had become more constrained. The ocean still held opportunities, but fewer lineages remained to explore them, and fewer evolutionary possibilities survived within those lineages. This makes the Smithian-Spathian transition more than another extinction layered into the Triassic record. It was a narrowing of possibility at the very moment the recovering ocean seemed richest. The survivors carried forward only a fraction of what had existed before the crisis, and that fraction became the foundation for later marine life. Across immense stretches of geological time, the descendants of those survivors would fill oceans with forms that could never have existed without this particular sequence of loss, survival, and renewal. Evolution did not preserve every experiment the recovering ocean had produced. Along the margins of the early Triassic seas, several of the strangest marine reptiles eventually disappeared, leaving behind no direct descendants. Hupehsuchus, Eretmorhipis, and Parahupehsuchus belonged to this early radiation, animals shaped for shallow Chinese lagoons where the newly opened marine world offered unusual opportunities. Their disappearance near the early to middle Triassic boundary marks not a failure of evolution, but a change in the conditions that had made their particular designs possible. As the seas became more crowded with hunters, specialization carried a different cost. Bodies suited to sheltered waters and distinctive feeding habits could work remarkably well, while competition remained limited. Yet those same adaptations could become restrictive when the ecological landscape shifted. The extinction of these forms narrowed one branch of the experiment, while another lineage continued refining the basic ichthyosaurian solution to life at sea. Among the survivors were the shastosaurids, animals whose proportions and swimming anatomy reveal a deeper commitment to open water. Their bodies became larger and more streamlined, reducing resistance as they moved through the sea. Instead of relying primarily on the sheltered environments occupied by earlier experimental forms, these ichthyosaurs were increasingly suited to sustained movement across broad marine spaces where endurance and efficient propulsion could determine whether a predator found enough food to survive. The change can also be read inside the skeleton itself. Fossils from the Agardalen area of Spitsbergen, in what is now Norway, include vertebrae from the early Spathian with highly cancellous internal bone structure. This spongy architecture reduced unnecessary mass while maintaining structural strength, a useful arrangement for an animal whose body was supported by water rather than by the ground. The bones preserve a physical record of commitment, showing that aquatic adaptation was not simply a matter of surface shape. It reached deep into the architecture of the body. Later, Triassic ichthyosaurs pushed this specialization even further. Their eyes became enormous in proportion to the rest of the skull, among the largest known in any vertebrate. Such eyes were particularly useful where sunlight weakened with depth, allowing these predators to detect prey in waters beyond the brighter surface layers. The change suggests an expansion of hunting space, from the illuminated shallows into a darker, vertical world where vision itself became part of the predator's equipment. Their increasing specialization also changed the meaning of size. A larger body could store more energy, support powerful swimming muscles, and travel farther between feeding opportunities, but it demanded a reliable supply of prey. Growth, therefore, became inseparable from the productivity of the recovering ecosystem itself, linking the evolution of the hunter to the recovery of everything beneath it. This refinement followed a broader ecological transformation. Early ichthyosauromorphs represented a remarkable collection of body plans, each exploring a different way of entering the sea. As marine communities became denser, however, broad experimentation gave way to increasingly specialized solutions. Selection favored animals capable of converting muscular effort into efficient movement, locating prey over greater distances, and exploiting parts of the ocean that other predators could not reach as effectively. The result was not immediate perfection, but a long narrowing toward forms that could perform one task exceptionally well. By the Middle Triassic, shastosaurid ichthyosaurs had become some of the largest animals in the sea, embodying a more mature version of the marine predator. Their descendants would eventually acquire the familiar streamlined silhouettes of later ages, but the essential transformation had already begun. The great dolphin-shaped hunters of the Jurassic and Cretaceous were not sudden inventions. Their bodies carried forward the accumulated refinements of an evolutionary experiment that had started among the first survivors of the devastated Triassic Ocean. The change can be felt most clearly in the architecture of the seafloor. After millions of years without the great reef systems that had once shaped entire marine provinces, complex reef communities began returning during the Middle Triassic. Their builders were no longer the dominant reef organisms of the Paleozoic. Scleractinian corals appeared as a new generation of reef architects, laying foundations that would eventually support the coral ecosystems familiar from much later seas. These first reefs were not yet perfected. Their structures were often reinforced by unusual organisms such as tubophytes and by large quantities of marine cement, binding loose material into more stable frameworks. Species richness remained lower than in the great Permian reef systems, yet the physical return of three-dimensional habitat changed the possibilities available to countless smaller animals. Cavities, surfaces, ledges, and sheltered spaces created places to feed, hide, reproduce, and hunt. A reef was not merely a structure, it was an expansion of ecological space. By roughly 244 million years ago, the Luoping biota of Yunnan province in China captured that expansion in extraordinary detail. More than 20,000 fossil specimens preserve fish, marine reptiles, invertebrates, and plants within a single ancient community. The assemblage reveals an ocean no longer defined by a few hardy survivors. Different body plans occupied different roles, and the relationships among them had become dense enough that individual fossils could preserve traces of interactions occurring throughout the food web. One such fossil belongs to a pachypleurosaur, a small sauropterygian whose hind limb had been amputated and marked by tooth impressions. The animal itself was a predator, yet something larger had attacked it. That single injured limb carries an ecological message more clearly than a list of species can. Predation was no longer confined to a simple chain from small prey toward a single dominant hunter. Predators had entered the diets of larger predators, creating additional layers above them. The same escalation appeared among animals with very different bodies. Sharks diversified through the Middle Triassic, and some new forms developed crushing teeth suited to hard-shelled prey. Their feeding style added another pressure to communities already responding to increasingly active hunters. Shells, burrows, mobility, and other defenses became parts of an ongoing exchange between the ability to consume and the ability to survive being consumed. Even the reefs themselves became part of this exchange. Their growing complexity created refuge for small animals, but refuge also concentrated prey, giving hunters new places to search. Every added layer of habitat could therefore support both escape and predation, increasing the number of possible interactions within the same space. The Middle Triassic Ocean was consequently different in more than its inhabitants. Its communities were increasingly connected, so a change in one population could alter feeding opportunities elsewhere, allowing ecological pressure to travel through the food web rather than remaining confined to one habitat or lineage. It possessed a deeper network of relationships, with reef builders supporting communities, small predators feeding on invertebrates, larger hunters pursuing smaller reptiles and fish, and apex predators capable of turning other hunters into prey. Evolution operated within this increasingly crowded web, where every successful adaptation altered the opportunities available to something else. By this stage, recovery had become something more permanent. The ocean was no longer reconstructing an older world piece by piece. It had assembled a new ecological system, one in which competition and predation were woven more deeply into the structure of marine life. The baseline had shifted, and the sea that emerged from the catastrophe carried a greater intensity within its very architecture. The ocean outside a modern coastline carries a history far older than the waves themselves. Beneath the familiar movement of fish, shells, and drifting plankton lies an inheritance shaped during the most severe biological crisis the seas have ever endured. The communities living there today were not simply restored from what existed before the Great Dying. They emerged from the survivors, the vacancies, and the evolutionary choices that followed. Consider the seafloor first. Bivalves became dominant after the extinction because their physiology endured the altered chemistry of the recovering ocean more effectively than brachiopods. That change never reversed. From tidal flats to deep marine sediments, clams, oysters, mussels, and their relatives occupy habitats whose modern character was partly determined by that ancient environmental filter. Their abundance is therefore not merely a feature of today's sea. It is an inheritance from a world that disappeared more than 250 million years ago. Above them, ray-finned fishes expanded through the newly reorganized marine food webs. Today, they account for roughly 96% of living fish species, encompassing salmon, tuna, cod, reef fishes, and countless smaller forms. Their extraordinary variety belongs to a lineage that passed through the Triassic recovery and continued diversifying as new habitats and feeding opportunities appeared. Every modern school of fish carries some trace of that long expansion. The same deep continuity reaches into the cephalopods. Squid and octopus relatives were already present during the early Triassic, preserved among the remarkable fossils of the Paris biota. They survived later disruptions, including the Smithian crisis, and remained part of marine communities through the ages that followed. A squid moving through deep water today belongs to a lineage whose ancient branches endured when much of the ocean's previous biological structure had vanished. Sharks followed another path through the same upheaval. Their lineage survived the Great Dying and diversified during the Triassic, gradually occupying new roles within increasingly complex food webs. The great white shark, hammerhead sharks, and whale sharks are separated from those early survivors by immense stretches of evolutionary time, yet their ancestry passes through the same rebuilt ocean. Their presence today is part of a continuity that began when the seas were being repopulated under unfamiliar conditions. Much later, mammals returned to the water. Whales and dolphins evolved their marine existence during the Cenozoic, long after the Ichthyosaurs had disappeared, but they entered an ocean whose basic ecological architecture had already been transformed. They became fast swimmers, deep divers, filter feeders, and active predators in roles that earlier marine reptiles had occupied. The bodies changed completely, while the ecological opportunities remained part of a much older framework. Even the smallest organisms carry this inheritance. Photosynthetic plankton form the foundation of marine food webs and contribute roughly half of Earth's atmospheric oxygen. Their communities, like those of larger animals, were reshaped by the biological and chemical disturbances surrounding the Great Dying. The microscopic life suspended through today's waters therefore belongs to an ocean whose foundations were repeatedly reorganized during the Triassic. Seen from any shoreline, the modern sea can appear timeless, yet its familiar inhabitants represent a particular evolutionary outcome, not an inevitable restoration of the Paleozoic world. The predators, shellfish, fishes, cephalopods, and plankton surrounding us are descendants of lineages that passed through catastrophe, bottlenecks, ecological vacancies, and repeated rebuilding. The ocean of today is not the ocean that survived the Great Dying, nor is it a simple continuation of that vanished world entirely. It is the ocean that life constructed afterward, layer by layer, lineage by lineage, until the ancient aftermath became the living world we know. Evolution is often imagined as a patient process, unfolding across immense stretches of geological time. Yet the early Triassic offers a different measure of possibility. Once the old ecological structure had been stripped away, evolution did not move at its usual pace. It accelerated into the vacant spaces, producing new bodies, new predators, and new relationships within only a few million years. At the extinction boundary, marine diversity had fallen so severely that many familiar ecological roles were scarcely represented. Then the rebuilding began. Within roughly 6 million years, an ichthyosaur lineage had produced an apex predator reaching 17 meters, about 56 feet in length. By roughly 8 million years after the catastrophe, a complex food web containing producers, invertebrates, fishes, cephalopods, marine reptiles, and enormous predators was functioning across several trophic levels. The scale of that transformation becomes clearer when compared with another marine invasion. Whales required approximately 15 million years to move from small terrestrial mammals into large ocean predators comparable in body size to Symbospondylus youngorum. Ichthyosaurs achieved a similar increase in body size in roughly 2.5 million years. Their expansion was therefore several times faster, unfolding while the ocean still contained vast areas of ecological opportunity. The reason may lie in what was missing. Modern ecosystems are crowded with established competitors. A new adaptation must compete with organisms already exploiting food, shelter, breeding grounds, and hunting strategies. Many evolutionary changes therefore encounter resistance before they can become widespread. In the recovering Triassic Ocean, much of that resistance had vanished. Empty ecological roles were waiting to be occupied. A mutation that allowed an animal to process a new food source, swim more efficiently, hunt at greater depth, or reach a previously unused body size could immediately open access to resources that few other organisms were exploiting. Natural selection did not need to displace a perfectly established competitor before favoring such innovations. The ecological landscape itself amplified their value. Each successful innovation also changed the environment around its inventor, creating fresh opportunities for other survivors. This makes the early Triassic resemble a natural experiment in evolutionary opportunity. The catastrophe created the conditions, and the surviving lineages supplied the raw material. From that combination came rapid changes in body size, feeding behavior, locomotion, and predator structure. Evolutionary history rarely allows such a process to be observed with such a clearly defined starting point, because most ecosystems are already too crowded for the contrast to be so visible. The same pattern appears elsewhere in the history of life. The Cambrian explosion followed an early expansion of animal diversity into newly accessible ecological possibilities. Mammals underwent extensive diversification after the extinction that removed the no-navian dinosaurs. In each case, ecological vacancy was followed by a burst of experimentation and specialization. The details differed, but the underlying opportunity was remarkably similar. What the Triassic reveals is that evolutionary rate is not a fixed property of life. It depends partly on the ecological resistance surrounding a lineage. In a mature ecosystem, novelty must find room among established competitors. In a devastated ecosystem, novelty can become the mechanism by which the ecosystem itself is rebuilt. There is an extraordinary asymmetry here. The first construction of complex marine ecosystems required hundreds of millions of years of evolutionary history. Yet, after the Great Dying, much of that lost complexity was replaced by something fundamentally new in only several million years. Recovery was not a reversal of time. It was a rapid act of invention carried out by survivors moving through an ocean with more empty space than any previous generation had ever known. The fossil record leaves behind an unusual kind of symmetry. Again and again, moments of extraordinary biological expansion appear after periods when entire branches of life have been removed. The pattern reaches far beyond the early Triassic. The Cambrian explosion followed the decline of the Ediacaran biota. The great diversification of mammals followed the extinction that ended the reign of no-navian dinosaurs. And the Mesozoic transformation of marine ecosystems unfolded in the aftermath of the Great Dying. Catastrophe does not merely interrupt evolution. By removing established communities, it can alter the conditions under which evolution proceeds. The relationship becomes especially clear when the scale of destruction is considered. Smaller extinction events generally leave more of an ecosystem intact, allowing surviving organisms to return to familiar roles. The largest marine extinction was different. It removed so many dominant organisms that entire ecological positions became available at once. The recovery, therefore, had unusual room to expand, and lineages that had previously occupied minor positions could suddenly become architects of major communities. Ichthyosaurs offer one of the clearest examples. Before the extinction, their ancestors did not possess the open ecological landscape that later allowed marine reptiles to diversify so extensively. The new ocean provided opportunities for swimming predators, deep water hunters, and large bodied marine reptiles that had not previously held those positions. Their later success was therefore connected to an absence created long before their descendants became familiar forms. Something similar happened with scleractinian corals. The reef systems of the Permian belonged largely to different organisms, and the extinction erased those ancient structures. In the Middle Triassic, scleractinian corals began constructing reefs of their own, eventually becoming the foundation of reef ecosystems that would persist for hundreds of millions of years. Every living coral reef, with its sheltering fishes and intricate communities, carries part of that evolutionary history within its architecture. The same principle reaches across the modern ocean. Sharks, cephalopods, ray-finned fishes, and many other groups survived the catastrophe and participated in the ecological rebuilding that followed. Their modern descendants inhabit communities whose basic relationships were profoundly reshaped during the Triassic. Even whales, which entered the sea much later, evolved within an ocean whose food webs and competitive structure had been transformed by events hundreds of millions of years earlier. This does not mean that the Great Dying was necessary for life itself, or that evolution was somehow moving toward the ocean we know today. There was no destination waiting beyond the extinction. The survivors were responding to immediate conditions, using whatever opportunities remained available. A different catastrophe would have removed different organisms, opened different ecological spaces, and favored different survivors. The resulting ocean could have been almost unrecognizable. That contingency is one of the most remarkable lessons preserved in ancient stone. The living ocean is not simply the product of gradual improvement, as though evolution had been constructing a better version of the same world for hundreds of millions of years. It is the consequence of countless accidents, disappearances, survivals, migrations, and ecological openings. Some of its most familiar inhabitants exist because particular ancestors happen to cross particular thresholds at particular moments. The Great Dying, therefore, stands at a strange intersection between destruction and creation. Its devastation narrowed life almost beyond recognition, yet the emptiness it produced became the setting for an immense evolutionary expansion. Over roughly 8 million years, new predators, new prey, new reefs, and new ecological relationships assembled from the survivors. The early Triassic was not rebuilding an ocean that had existed before. It was producing a different one without intention or direction through survival and reproduction in the spaces left behind. Much of the ocean that surrounds us today is the distant result of that process, a living world shaped not only by what survived, but by everything that disappeared. Stone has become a kind of archive, not because it was designed to preserve the past, but because fragments of vanished worlds sometimes survive long enough for another species to find them. Limestone, siltstone, shale, and ancient sediment hold traces of organisms that lived hundreds of millions of years ago, preserving bones, shells, teeth, and chemical signatures within layers that can be read like pages. From these physical remnants, scientists reconstruct an ocean that no human ever entered. A nearly complete skeleton of Cartorhynchus, discovered near Chaohu in China, offers one example of how much information a single fossil can contain. The angles of its bones reveal unusual flexibility in the wrists, while the density of its skeleton and shape of its flippers preserve evidence of an animal adapting to life in water. Nothing about the specimen describes its existence in words. The anatomy itself becomes the evidence, allowing its place in the early history of ichthyosaurs to emerge from the arrangement of bone. In the Augusta Mountains of Nevada, the teeth of Thalattoarchon preserve another kind of record. Their cutting edges remain distinct after roughly 244 million years, allowing their geometry to be examined in detail. Tooth shape reveals feeding behavior because different prey impose different mechanical demands. The broad ecological role of this predator can therefore be inferred from structures that once met living flesh beneath a vanished sea. Other fossils preserve something closer to a crime scene. Two specimens of Tanistropheus were found with their skulls separated from their vertebral columns, while tooth marks on the bones provide clues about what happened after death. The spacing and form of those marks can be compared with the jaws of predators known from the same rocks. Paleontology becomes forensic work across immense stretches of time, reconstructing an interaction that occurred long before any human eye existed to witness it. Chemical evidence extends the record beyond what anatomy can reveal. Boron isotopes, preserved in fossil shells, can provide estimates of ancient seawater acidity, turning tiny differences in elemental composition into measurements of an ocean whose acidity no instrument ever recorded. Oxygen isotopes preserved in conodont teeth can preserve information about ancient water temperatures, allowing scientists to trace changes across intervals when coastlines, continents, and entire ecosystems were radically different. Even molecules can survive. Molecular fossils derived from ancient pigments and other biological compounds can identify organisms that left little recognizable body material behind. Sediments can therefore preserve not only the shape of vanished creatures, but chemical traces of the communities in which they lived. Each method adds another layer of resolution, allowing anatomy, chemistry, sedimentology, and geologic age to converge on the same ancient world. This ability belongs to a remarkably unusual point in the history of life. Other animals have sensed their surroundings, adapted to changing conditions, and inherited information from their ancestors, but none has reconstructed an ecosystem that disappeared long before its own existence. Human beings can examine a fossil, measure an isotope ratio, compare layers across continents, and assemble evidence into a history of events no living observer witnessed. The ichthyosaurs themselves possessed no such record. They hunted, reproduced, competed, and eventually vanished without knowing that the ocean around them had been transformed by an extinction millions of years earlier. They experienced their world only as the present. We inherit something different. In every fossilized bone, every preserved molecule, and every chemical signature locked inside ancient stone, the past remains available for examination. The living ocean is not an isolated moment. It is the latest expression of a history that can still be traced, layer by layer, through the rocks beneath our feet. Somewhere beneath the surface tonight, the ocean is carrying on arrangements that began hundreds of millions of years ago. Predators move through layered food webs, filter feeders draw nourishment from passing water, and larger hunters occupy the highest levels of their communities. The species have changed beyond recognition, yet the ecological positions themselves can persist across immense stretches of time. An orca moving through modern seas occupies a role remarkably similar to that once held by Thalattoarchon. Both belong to the uppermost tier of marine predation, where large vertebrate hunters shaped the behavior and distribution of animals below them. Their bodies were different, their lineages separated by vast geological intervals, but the ecological opportunity was comparable. The early Triassic helped establish a new arrangement of marine life in which large, active predators could dominate open water food webs. Far below the reach of sunlight, squid continue another ancient thread. Their lineage passes through the early Triassic, including the remarkable cephalopods preserved in the Paris biota, and extends through later crises and radiations. Jet propulsion, grasping arms, and movement through open water belong to a body plan that has endured through repeated transformations. A squid, drifting through the deep ocean, therefore, carries an inheritance older than most familiar marine ecosystems. Reefs offer an even more visible connection. The corals building structures across the Indo-Pacific, the Caribbean, and the Red Sea descend from scleractinian lineages that became important reef builders during the Middle Triassic. Their ancestors entered an altered seafloor and began constructing living frameworks where earlier reef communities had disappeared. The modern reef, with its sheltering fish, grazing animals, predators, and microscopic partners, is a vastly elaborated descendant of that early architectural experiment. Nearby, a shark moves through the same kind of habitat with a lineage that reaches even farther back. Sharks had already established themselves as marine predators before the end Permian catastrophe, survived the extinction, and continued adapting as the ocean changed around them. Their persistence is part of the reason the modern sea contains predators whose ancestry crosses multiple mass extinctions. The continuity becomes easier to sense when measured against the age of the ocean itself. Earth has held oceans for roughly 3.8 billion years. Across that immense interval, life has passed through 5 major mass extinctions, each removing established communities and leaving survivors to reorganize what remained. The present ocean is therefore not simply an ancient environment that endured intact. It is the accumulated result of repeated destruction, migration, adaptation, and ecological invention. The Great Dying remains one of the deepest turning points within that history. 252 million years ago, it removed so much marine life that the survivors entered an ocean with unprecedented ecological vacancies. During the roughly 8 million years that followed, new predators, prey, reefs, and food webs emerged from those openings. Their descendants did not inherit a finished world. They inherited opportunities, and evolution filled them in countless different ways. Tonight, the process continues without any awareness of its age. Deep water circulates, nutrients rise, plankton capture energy, predators pursue prey, and countless organisms reproduce within systems that stretch beyond the span of any individual life. The ocean remains ancient, but it is never merely repeating itself. Every generation modifies the living structure it receives, adding another layer to a history already measured in billions of years. From a shoreline, the sea can seem like a single expanse. Beneath that surface lies a lineage of relationships extending through vanished oceans and extinct worlds, connecting the living present to a time when almost everything familiar was absent. What surrounds us tonight is both ancient and newly made, a world assembled through survival, transformed through competition, and still carrying the distant imprint of the catastrophe that changed its course.